This is Chemistry 3053. Today we're going to start on David Klein's Chapter 4, Alkanes and Cycloalkanes. So I'm trying a little bit different format this time, and we'll see how this works. So, first slide's on alkanes. You can see this, actually on this slide, there's only one alkane that is shown. That's ethane. Ethylene or ethene, acetylene or ethine, and then benzene. These are not alkanes. This is an alkene, alkyne, and then arene. So ethane is the only molecule here that's on the first slide that is an alkane. However, these are all hydrocarbons, which have only hydrogen and carbon. Alkanes are saturated. Alkenes, alkynes, and arenes are unsaturated. This means that they do not contain all of the hydrogens that they could. You could still add H2 across this double bond, or H2 twice across that triple bond, or H2 across each of these three double bonds. You're going to see that we have, and have had for decades, two nomenclature systems. We've been switching from the common name system to the IUPAC system for probably 50 years or maybe more, but we chemists change slowly, and so we still have a lot of common names in our used in a lab, and not so much in journals anymore, but a lot in lab. And so the IUPAC has a formal set of rules. International Union of Pure and Applied Chemistry, that's IUPAC, and those are the rules that we're going to learn for alkanes in this chapter. The IUPAC name is preferred, actually, and when you submit a paper to a journal, you're asked to convert any of your common names that you're using, such as if you're using acetone, you might be asked to rename it propanone. What you're going to see is we're going to cover chemistry in the form of families of compounds. So the first family that we're covering is alkanes. Then we will cover alkenes. Then we will cover alkynes. And then we will cover alcohols and ethers. And we're going to just sort of march through the different families of compounds. And these are going to be families that all have a common functional group, or in the case of alkanes, they have no functional group. And so they will have similar characteristics and can be compared very well inside families. When you start making comparisons, you're going to have to watch the number of things that you change at once. So in other words, you would not want to compare or try to compare, say, an alkane that has 6 carbons with an alkene that has 8. You're going to want to change just one thing at a time in making comparisons. But the important thing pertinent to the nomenclature is you're going to learn the nomenclature rules for alkanes, and then you're going to see that the nomenclature rules for alkenes or alkynes or alcohols will use those same rules that you learn for alkanes and just build on them a little bit. And so the nomenclature for alkanes will probably be the most complex that you're going to learn. And then when you learn the nomenclature for alkenes and alkynes, alcohols, etc. You'll just have to draw up these rules that you're learning here. And so it's going to be very important that you learn these rules. And you're going to want to work a lot of the problems in your textbook. There's just not time for me to work them here for you. So you'll have to be able to know the parent name. You'll look at the longest carbon chain. You'll have to name the substituents when there's branching. And you'll have to tell the location of the substituents, what position the substituent is in along the carbon chain. And that's what we're going to do right now. So, first you identify the parent chain. This is the longest chain, and so you can see it identified here. It's outlined in red. And so it would not be this way because this is the longer chain. And so you could actually go to this carbon instead of that carbon if you wanted. It doesn't matter. This methyl is the same as that methyl. Over here, this one you see is the exact same structure as that, but here this one is outlined in red, and this one is wrong, even though they both have the same number of carbons in the longest carbon chain. You also want to have the highest number of substituents. This one has 3 substituents. This one has only 2 substituents. So this is the correct carbon skeleton, the correct parent chain to use. That's the reason for this is because you want to keep the substituents as simple as possible in naming these. So this is a table from your textbook, and you will want to know this table, at least 1 through 10, at the very least. Some of these others, 11 through 15, it might be good for you to learn, but at least you'll need to know this. It will be assumed, everybody will assume that you know this. So meth is the parent name for methane. So what you're going to see is that when you have this stem, or the parent name, meth, you will obtain the name of the alkane by simply adding A-N-E. So think of it like this. Alkane ends in A-N-E. So to meth, you will add the suffix A-N-E. For eth, you will add A-N-E. For prop, you will add A-N-E. And it's the same way all the way down. Now, when we get into alkenes, you're going to see that instead of adding A-N-E, if it's an alkene, you will add E-N-E. There won't be a possibility up here because an alkene has to have 2 carbons in it in order to have a double bond. So the smallest alkene you'll have will be ethene, propene, butene, pentene, hexene, heptene, octene, nonene, decene. And so you're going to have to know these because you're going to be using them in every family of chemicals. You will have to know these. So this is something that you're going to be learning for alkanes, and you're going to be carrying it forward throughout Org 2 even. So learn this. It's table 4.1. So you have identified the parent chain, the longest consecutive chain of carbons, which contains the greatest number of branches. If the compound is cyclic, you will simply put the word cyclo in front of it. So this contains 3 carbons, and it's a cyclic compound, cyclopropane. 4 carbons, cyclobutane. 5 carbons, cyclopentane, etc., etc. So naming the substituents, notice the same stem, meth, eth, prop, but. Now, to name a substituent, you simply put YL at the end of that stem. So now it is methyl, ethyl, propyl, butyl, pentyl, hexyl. You're going to have to learn the names of your stems. So these correspond to that number of carbon atoms in the substituent now. We're talking about substituent, not the chain, not the backbone or the parent. So here you can see that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is decene. Decane. So 10 carbons, this is a decane. So you have some substituents, and so it's going to be, the name will be something, 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 decane. And so you identify the substituents, and you can see that you have a substituent with 1 carbon, so it's methyl. Here you have a substituent with 2 carbons, it's ethyl. Here you have a substituent with 3 carbons, this is propyl. And so this is going to be named in alphabetical order: ethyl, methyl, propyl, decane. Now we have to add in the positions where these are located. And so that's what we're going to do in the next few slides. So that is not quite all of the name, ethyl, methyl, propyl, decane. You're going to have to say X ethyl, Y methyl, Z propyl, where it will tell the positions of those substituents along the carbon chain. A ring, back to rings now, can be either a parent or a substituent, depending on the relative sizes. So it's actually preferable to name the ring as the parent. And so that's what you do. So here this is cyclohexane. So this is 1, 2, 3. So this is going to be propyl cyclohexane. However, in those cases where the substituent has fewer carbons than, in which the ring has fewer carbons than the acyclic part, then the acyclic part becomes the parent. So this is cyclopropyl butane, because this has 3 carbons and that has 4 carbons. If you had a situation in which the number of carbons in the cyclic part is equal to the number of carbons in the acyclic part, then you will name it as like this one, where the cyclic part is the parent chain and the acyclic part is the substituent. In cases where you have substituents with complex branches, here notice this is a complex branch, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is going to be something undecane, okay? And this is going to be the something. And so it's 1, 2, 3, 4. And so this is going to be a butyl substituent with a methyl in the second position, so at the second carbon. So you will start numbering these carbons at the carbon that is attached to the long chain, the parent chain. So this is numbered 1. You don't start numbering at this end. You start numbering at the carbon that's attached to the longest chain. And now, so this is 1, 2, 3, 4. So this methyl is at the 2 position. So the name of this substituent is going to be 2-methyl-butyl, because this is a substituent. It's not a compound. It's 2-methyl because the methyl is in this 2 position, and it's butyl because this has 1, 2, 3, 4 carbons. So this is 2-methyl-butyl. This is the 2-methyl-butyl substituent. So you can see the name of the substituent is 2-methyl-butyl. And going through your textbook, you will see that whenever they name these, they put these, the author has put these in parentheses. And that is because when it's actually written into the whole name, this is kept in parentheses. If it's sort of a complex branching in the substituent. And that is not given very often in your textbook. I think the only example I saw of it was in the answer key to problem 413 or 414, something like that. They do give you that. So I have added this you won't find in your textbook. The actual name of this compound is, remember, it's undecane. This is an undecane because it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons. And so this is in the 6th position. 1, 2, 3, 4, 5, 6, or you can count from this end. 1, 2, 3, 4, 5, 6. So this substituent is in the 6th position. So this is 6-2-methylbutyl undecane. And so this is the actual way that you write this name, and it's not given in your textbook, but it's given here. So you have this example for you. Some branch substituents have common names that you will see used in your book. So you have propyl, which is an IUPAC name, but the branched propyl group, where the attachment is at the internal carbon. Here the attachment is at the terminal carbon of the propyl group. Here it's at the internal carbon of the propyl group. And so the attachment here is at the central carbon. And so this could be named as an ethyl with methyl at the 1 position. So this could be named 1-methyl-ethyl, and notice that it is in parentheses. Or this could be named using the common name system, in which this would be called isopropyl. So this is the IUPAC system. This is the common name system. Okay? You're going to see that this iso means that you have this characteristic CH3, CH3 group. The iso typically designates CH3, CH3. And in the very old chemistry journals, you will see iso even used in names for branched hexanes and pentanes and heptanes, and so you see isohexane, isopentane, isoheptane, and that just became so confusing that has fallen into disfavor, and you don't see it so much unless you actually have to go back and read something in the older literature. So these things do change, but they change very slowly. So isopropyl, this is very commonly used, and this is what you're going to see most frequently used in your homework. And so learn it, isopropyl, isopropyl. There are 3 types of branched butyl groups. So there is the straight chain butyl. Then there is the sec-butyl, isobutyl, and tert-butyl. Notice the isobutyl has this CH3, CH, CH3. The iso tells you that you have that same branching that you saw in isopropyl. So it's the same as isopropyl, except you have this CH2, this methylene group here. Now, sec-butyl and tert-butyl, a lot of times students get these confused. The way that you tell this is that this is a secondary carbon atom. That means you have 2 other carbons attached to this carbon that is attached to the parent compound. The tert-butyl, this carbon atom that is attached to the parent compound, is a tertiary carbon. That means it has 1, 2, 3 other carbons attached to it. So here the sec and the tert both are designating what type of carbon atom is attached to the parent. This is a secondary carbon atom, so it's called sec-butyl. This is a tertiary carbon atom, so it's called tert-butyl. So sec-butyl, isobutyl, tert-butyl, those are all three common names, and these are the IUPAC names for the alkyl groups. So this is 1-methyl, because the methyl is attached to the 1 carbon atom, 1, 2, 3, 1-methylpropyl. Here, this is a methyl attached to the 2 carbon, 1, 2. So this is 2-methylpropyl. And here, this is 1,1-dimethyl ethyl. So both of these methyls, this and this, are attached to the 1 carbon, because we start numbering at the carbon that is bonded to the parent chain. So this is an ethyl group bearing 2 methyl substituents. So 1,1-dimethyl ethyl. And notice they are all in parentheses, because when this nomenclature system is used, they will be in parentheses in the IUPAC name. One last thing I think I should point out, because this is part of the name. You'll notice that sec of sec-butyl and tert of tert-butyl are in italics, and there is a hyphen between sec and butyl. There is a hyphen between tert and butyl. Sometimes this is abbreviated as just an italicized S-butyl or T-butyl. But iso is actually part of the name, okay? Iso is part of the name. It is not in italics. There is no hyphen here, and so you're going to see later on, it's going to be very important. The first letter of this name is considered to be I. The first letter of this name is considered to be B. The first letter of this name is considered to be B. So this becomes very important. It's not italicized, not hyphenated. And let's go back and look. Let's go back. Let me see if I can get this to go back. Yes. Do you notice here in isopropyl, there's no hyphen. This is not italicized. So there's the pattern that you have. And this may seem trivial to you, but it becomes very important later on. So when you're trying to enter these things into your homework, you'll need to enter them just like this. And then butyl has nothing in front of it, because this is just a straight chain butyl group. So this says 3 types of butyl groups. Actually, there are 4. There's 3 types of branched butyl groups. If one substituent is present, number the parent chain so that the substituent has the lowest number possible. So here you can see that this methyl group is very near the end of this molecule. This end of the molecule, so obviously you're going to start numbering from the end farthest away from me. 1, 2, 3, 4, 5, 6, 7. This is the correct numbering. Here you could say, well, why don't we start numbering at this end? 1, 2, 3, 4, 5, 6, 7. This would put the methyl in the 6th position, and it would be wrong. So this is correct. This is incorrect. This is a very simple example. When multiple substituents are present, you number the parent chain to give the first substituent the lowest number possible. So 1, 2, 3, 4, 5, 6, 7. So here you have, when they say first substituent, this substituent is in the 2 position. That's what they mean by first position, first substituent. So here you could number this as 1, 2, 3. So these would be, both of them, or one of them, would be the first substituent that you encounter in numbering down the straight chain. So here the first substituent would be at the 3 position. Here the first substituent would be at the 2 position. So this is correct because the lowest numbered substituent is 2. Here the lowest numbered substituent is 3. And so you use the one that has the lowest numbered substituent. 2 5,5. And this is going to be trimethyl heptane. Okay, so you can tell straight off at the beginning, you identify your longest chain. This is going to be a something, 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 something heptane. Then you can see that you have 3 methyls. It's going to be a trimethyl heptane. And then you have to determine what are the positions. And so this is going to be 2,5,5 trimethyl heptane. And that's the full name. Okay, what if the 2 substituents would have equally low numbers and there's no other way to differentiate? Then you simply use alphabetization. So chlorine comes after bromine. C comes after B in the alphabet. And so bromine takes precedence over chlorine. So this is bromo, this one is chloro. So this would be, the correct name would be 1-bromo, 5-chloro, pentane. You can see this is a pentane. 1, 2, 3, 4, 5. So you know straight off this is going to be something, 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 pentane. You look at your substituents, it's going to be a bromo, chloro, pentane. Then you can find the numbering. You know this is going to be a 1-bromo, 5-chloro, pentane. To assemble the whole name, you put the number and name of each substituent before the parent. So these are prefixes. The number and the chain, the number and the name of each substituent is a prefix. And you put them in alphabetical order, as you've seen me do a few times. A prefix is used, di, tri, tetra, penta, if multiple substituents are identical. Di or tri is ignored when alphabetizing the substituents, and so are sep and tert. Whatever it is that's in anything in italics is ignored. Identify the parent chain. Identify and name the substituents. Then you start putting it together. Number the parent chain. Assign a locant to each substituent. List the numbered substituents before the parent name in alphabetical order. So you've seen me do that. You'll have to work your homework problems and check your answers in the study guide and solution manual. Okay, bicyclic compounds. Bicyclic compounds are a little bit more difficult. Bicyclic compounds, so these are the ones that have 2 rings that are fused. And so the carbons here, I don't know if you can see it, here and here are the bridgeheads. Those are the points where the 2 rings are fused, here and here. And so there are 3 bridges, 1, 2, 3. Those are the 3 bridges. This is what they're talking about when they talk about the paths. Those are the bridges. You count the number of carbons in each one. So this one has 2 carbons. You don't count the bridgehead in the bridges. Okay, so this bridge has 2 carbons. That bridge has 2 carbons. This bridge has 1 carbon. And you can see it here. 1, 2, 1, 2, 1. And so the name for this compound is it's bicyclo. Bicyclo goes in front of the name. And so this is 1, 2, 3, 4, 5, 6, 7. It's going to be a something, something, something heptane. And you can see that this has 2 fused rings. So this is going to be a bicycloheptane. And now you have to be able to tell, exactly the sizes of the bridges, because this is a bicycloheptane as well. This is a bicycloheptane. So you have to be able to differentiate between these 2. And the way that you do that is you tell the sizes of the bridges. So this bridge has 2 carbons, this bridge has 2 carbons, and that bridge has 1. So this is 2, 2, 1. And you put them from the highest number to the lowest number. Over here, this one is 1, 2, 3, 1, 1, 3, 1, 1. That tells the sizes of the bridges. You put them from highest to lowest. And so that's how you differentiate between the 2 bicycloheptanes. So this ends the first part. So this would be the end of day 1 lecture.